Class example 3.53. For each of the scenarios below, construct an equation that models the amount of some quantity y after t units of time. So for these questions, it's going to be useful to keep our general equation in mind, where a is going to be the initial amount, b would be the multiplier or the growth factor, and our p-value in this case is going to be the period in which b is applied. And we'll talk more about that as we go through the questions. So number 1 says 100 bacteria are present in a culture which is doubling in size every day. So y is equal to 100, our initial population, times 2 for our growth factor because it's doubling, and then just to the power of t because it's doubling every day. And if you like, it still follows our equation above because you could write this as over 1. That's how many days it is for it to double. So part B says use your equation to determine the amount of bacteria after 5 days. So in this case, we just replace our t with 5 to get 3,200. Number 2, 100 bacteria are present in the culture, which is tripling in size every day. So we're still starting with 100 for our initial population. But now, since we're not doubling, we're tripling, then our multiplier or our growth factor becomes 3. And then we're still just to the power of t because it's doubling every day. Number 3, 100 bacteria are present in a culture, which is doubling in size every 3 days. So this is going to change up our exponent a little bit. So again, the initial population is 100. We're doubling. But now, following our equation above, our p-value is the period in which b is applied. So we are doubling, so that's why we have 2 for our b-value. And then it's every 3 days. So you can imagine, if you start playing with this a little bit, if 3 days went by, if you replaced your t with 3, well then that would be 3 over 3. That would just be 1. So that would just be 200, right? 100 times 2. Makes sense? If your t value is 6, well that would be, so 6 days go by, well then it doubled 2 times, because this could really be replaced with just to the power of 2. So that would be 100 times 2, which is 200, times 2, which is 400. And then again with 9, so 9 days go by, that means that 3 doubling periods have occurred. And then 4 doubling periods have occurred. Number 4, 100 bacteria are present in a culture that is decreasing in size. The half-life for the amount of bacteria is 5 days. So y is equal to, well again, we're going to start with 100. But now, since the half-life is 5 days, we have to use 1/2 for our multiplier. And now it's going to be every 5 days. So our p-value in the equation becomes 5. And we could try this out, right? So if we think about this, this would be saying after 5 days goes by, then our exponent would become 1. So that would be 100 times 1/2. So you'd have half of your initial population. You'd have 50. If 10 days goes by, then that would be 2. So that would be like going 100 times 1/2, which is 50, and then times 1/2 again, which is 25. And maybe you can see the pattern. Number 5, 150 bacteria are present in a culture. Every 4 days, 75% of the bacteria remain. Okay, so y is equal to the initial population of 150. And now, let's just be careful in this one because it says 75% of the bacteria remain. So we're going to see below that, like some of the questions that we have a little later on, that the remain is a big word there because our multiplier will be 0.75 because I actually want 75% to be there. That would be different if it said is reduced by 75%, right? Because that would be only left with 25%. So just careful on the wording is really why I bring that up. And it's every 4 days that it's reduced by 75%, so t over 4. Number 6, a $1,000 investment is made that will earn 4% per year. So initial amount, we are going to be multiplying by 1.04, which is, this part of it is 0, or is 4% written as a decimal. And every year, so you could say it's t over 1 if you like, but that's really just the same thing as t. Uh, 6b, use your equation to determine the amount of money after 5 years. So now in this case, we just really replace our t with 5. Number 7, the initial population of a country is 25 million and is forecast to grow by 1.4% per year. So our initial population is 25 million. And our multiplier would be 1.014. And it's per year, so if you like, you could write it as over 1, but that's kind of weird. You'd probably want to just write it as t. Number 8, a $40,000 new car will depreciate in value by 12% per year. So if we start off with a $40,000 vehicle, then we're going to depreciate by 12%. So just careful on that, right? Because 100% would be 1. That's where you'd start, where nothing would change. If it was 40,000 times 1, you're still at 40,000. But if it's going to depreciate by 12%, that means you're going to be subtracting 12%. So you're going to be left with 88%, 1 minus 0.12. And then it's per year. So there's our final equation. Number 9, a $40,000 new car will depreciate in value by 30% every 3 years. So starting off with 40,000, it's going to be depreciating by 30%. So now we're going to have 70% at the end of each period. But now just be careful in this because it's depreciating by 30% every 3 years. So our denominator in that fraction would be 3. Number 10. A $1,000 investment is made and it earns 5% annual interest, compounded semi-annually. Determine an equation that models the value after t years. So note, semi-annually means twice per year or once every half year. So as always, we'll start with our 1,000 or our initial amount. Now let's explain this part. So if we go back up to, let's say, 6, where we were earning 4%. Well, we started with 1, and then we added the 4%. That's really the basic layout of this as well, where we start out with 1, and then we're going to add, well, typically we would add 0.05. That's what we would normally do if it was compounded annually, if it was compounded once per year, because the interest rate is 5% for the year. But we can't assume that we pay 5% on each of those periods because it's compounded semi-annually. So what we have to do, we have to divide this interest rate by 2. We're only really going to be adding 25%, right? Because in that half year when they looked at it, it was half of 5%. So that's why we're dividing by 2 here. So in the end, the number would be 1.025 for our multiplier. And then for our exponent, we're still going to have our time, but you can think about it as our denominator here. Our period in which this is occurring is happening every half of a year.